Hello everyone, welcome back. We're going to jump back into 4.5 and we're looking at a cost function that is not linear. Okay, in the last video we saw a linear cost function and we said increasing production will decrease average cost. Let's see what happens here. All right, so here's my cost function. I'm going to find the marginal cost function and the average cost function. Okay, remember that the marginal cost function is the derivative of the cost function. So here it's polynomial, so we can basically apply the power rule, constant rule. So when I find the derivative, I get 0.03q squared minus 1.2q plus 13. Okay. The average cost function, if you recall, is basically dividing all of the terms of the cost function by q. So when I divide each term, I'm basically dividing out a q. So I end up with 0.01q squared minus 0.6q plus 13 plus 1,000 divided by q. Okay. Now, this can get a little confusing and tricky because if you look what happened here in the derivative, my powers decreased by 1 in my marginal cost, but that's because I was using the power rule. I was taking a derivative. In the average cost function, my powers decreased by 1, but that's because I was dividing out a q. So the powers here decreased by 1, but I was not taking a derivative. Okay. All right. So let's talk about. Okay. So if we're at the one item production level, the marginal cost is $11.83 per item, which means to produce the next item, it's $11.83. Average cost of producing one item is $1,012.41 to produce that one item. So my per item cost is way more than my marginal cost. So the idea here is to lower the average cost, we're going to need to make more than one item, which implies that our quantity Q has to be greater than 0. Okay, so let's come down here and let's talk about what if we make 100 items. Okay, so my marginal cost for 100 items is $193 per item. So to make the 101st item, or the next item, would cost us $193. Okay, the average cost for the at 100 item production level is going to be $63 per item. Okay. So I can see here that if I make that next item, my marginal cost is $193. My average cost at 100 items is $63 per item. So I can see here that my marginal cost is greater than my average cost. So not a good idea to make another item because it's costing us more per item. It will raise our average cost. So the idea here is then that we should decrease production to lower our average cost. Okay, so let's talk about that. So if we make 100 items, each item costs $63 on average. Okay. But the 101st item, oops, will cost $193. So if we increase production, at the average cost will increase. And we don't want that. It's kind of like in class. If you take a test and the class average is 74%, and then one more person in the class takes the test and they get an 85, that's going to raise that test average. So it's the same kind of idea is in raising average cost. So here's kind of the rules, the main idea here. If we want to lower average cost or lower the cost per item, if marginal cost is greater than average cost, then we need to decrease production in order to lower our average cost. If marginal cost is less than average cost, then we will increase production. So that's the rule of thumb. Okay, so let's look at another situation, another company, no fixed costs this time. So there's no constant out here, okay, no fixed cost. And we're saying our production level is positive because if Q is equal to 0, then we would be dividing by 0 and we couldn't find average cost then. Okay, so we have to be producing we have to produce at least one unit or item in order to talk about average cost. All right, so let's find our average cost function, which basically means divide by Q. So you're going to divide each term of your cost function by Q. So my average cost comes out to be 0.01 Q squared minus 0.6 Q plus 13. Okay, and let's look at our marginal cost. Remember, marginal cost is the derivative of the cost function. All right, so if I take the derivative, I get 0.03 Q minus 1.2 Q plus 13. Okay. So let's look at some numbers here to get kind of an idea of how we're going to come up with a way of minimizing our average cost. All right, so what if I say I'm going to produce 10 items? Okay. So my average cost per item, I'm basically going to plug in 10 into my average cost function, which is going to give me $8 per item. So you can do that substitution. Okay, my marginal cost, if I'm producing 10 items, when I substitute that in here, whoops, I lost the square. Sorry about that. I am going to get a marginal cost of $4 per item. Okay, so look what's happening here. The marginal cost, the cost to make the 11th item is $4. The average cost per item is $8. So since marginal cost is less than average cost, we're going to increase production. All right, so we said marginal cost is less than average cost. Okay, so let's check that out. Let's look at what if I increase production to 11 items. The average cost for 11 items, if I substitute that into my average cost function, gives me $7.61 per item. So I can see that my average cost has gone down from $8 to $7.61. Okay, so now let's look later down the road. Okay, so we've increased production. We're going to take a look at it now and we're going to say, okay, how about, so later on, we're going to reanalyze our production level. And we're going to say, let's say if we produce 40 items, okay, the average cost is $5 per item. The marginal cost for 40 items is $13 per item, okay? So now in this situation, I can see marginal cost is 13. So if I produce another item, it's $13. Whereas my average cost per item is $5. So since marginal cost is greater than average cost, what should we do? We should decrease production. To lower average cost. All right, let's double check and make sure that seems reasonable. Okay, so let's decrease from 40 items to 39 and see what happens. So my average cost for producing 39 items is $4.81 per item. So I did decrease. I went from an average cost of $5 to $4.81. Okay, so what are we interested in here? We're interested in when our marginal cost is equal to our average cost. That seems like that would be the ideal production level where we would have the lowest possible average cost or cost per item. Okay, so what we really want is to know when is our average cost equal to our marginal cost. So what we can do is we can take those cost functions. This is my average cost function, and this is my marginal cost function, and we can set them equal, and we can solve this equation algebraically. Okay, so when I do that, we know we want to gather like terms, but one thing I notice is I can get rid of these 13s on each side. So I have 0.01 q squared minus 0.6 q on the left, and I have 0.03 q squared minus 1.2 q on the right. Now, we can solve it like this, but decimals gets a little messy and tedious. So one idea is to get rid of the decimals. So since I have 2 decimal places is the most, I'm going to multiply both sides by 100. So it moves the decimal 2 places in each decimal. So I end up with 1q squared minus 60q is equal to 3q squared minus 120q. And now it's much nicer to solve. And I can see it's a quadratic equation, so I want to gather my like terms on one side. I'm going to put everything on the right side since my q squared term on the right is larger and it's positive. So if I get rid of everything on the left and move it over to the right, I end up with, I have 3q squared minus 1q squared is 2q squared. I have negative 120q plus 60q is negative 60q, and that's equal to 0. And then I can see that this is a quadratic, but a quadratic equation. Remember, our one method, one of our most favorite, most useful methods in this class is greatest common factor. So we need to factor out the common factor here. Greatest common factor would be 2q. So I'm left with q times 30. And we set each factor equal to 0, and we solve to get our solution. So we get q is 0 or q is 30. We know q can't be 0 because we can't talk about average cost, and we said that q had to be positive. So I'm saying a production level of 30 items is when the average cost would be equal to the marginal cost. All right, so, and that means our average cost should be at a minimum. So let's double check that. Let's put some numbers into our average cost function and see. Let me move this up here. Okay, so let's check. So if Q is my optimum level, then I'm sorry, 30, then let's check below and above just to see that 30 would be the lowest. So if I say, what's my average cost at 29? What's my average cost at 30 items? And my average cost at 31. So if you want, you can pause the video, substitute those values into our average cost function, and see what you get. So at 29 items, the average cost is $4.01 per item. 30 items, the average cost is $4 per item. And at 31 items, the average cost is $4.01 per item. So we can see here then that at 30 items, we minimize average cost. To $4 per item. Okay. Now, there's another way to look at that. Think about how we minimized and maximized things in the past. Okay. We said we want to find that Q value, that production level that minimizes average cost. Well, we spent a lot of time in sections 4.1 and 4.3 minimizing or finding the local minimum or global minimum values of functions. So ultimately, what we're trying to find is the global minimum of the average cost function. Okay, which is what we did in section 4.3. So we're looking at our domain. Our domain is Q has to be positive. So we're talking about all real numbers greater than 0. All right, so how do we find those global minimums or local minimum? We use the derivative. We've never found the derivative of average cost. We've always been finding the derivative of the cost function. So let's find the derivative of the average cost function, which gives us 0.02q minus 0.06. All right, so to find the minimum is where our derivative is equal to 0. So we're going to set that derivative equal to 0 and solve for q. Better fix this 0.6. And we get q equals 30, which we already knew. We already knew that because we knew that the marginal cost at 30 is equal to the average cost at 30. We checked that in the last example. Okay, so this is our critical point. So if we want to show that it is a minimum, then we can do our first derivative test. Okay, so like I said, we used our derivative. We set it equal to 0, found our critical point, and we get that value that we talked about making average cost equal to marginal cost. That would be a critical point of the average cost function. Okay, so we'll do our first derivative test. Wow, technical difficulties. Let me bring my average cost, my derivative down here so that I can see it. 0.02Q plus 0.6. Okay. So remember our domain is from 0 to infinity. My critical point is at 30. So I need to choose a test value in each of these intervals. So I'm going to choose 20 and 50. And I need to plug that into my derivative. Okay, so I want to know if the derivative of the average cost is positive or negative on those intervals. Okay, so if I substitute 20 in, I'm going to get a negative value. If I substitute 50 into my first derivative, I'm going to get a positive value. So what does that tell me about my average cost function? On the interval from 0 to 30 means a production level between 0 and 30. My average cost is decreasing. At a production level greater than 30, my average cost is increasing, which I know means that this is a local minimum. But how do I know it is the global minimum? Well, if you recall back to section 4.3, when we talked about if we only had one local extrema over the domain, so one local extrema, meaning max or min, we have one local min. If that's the only one over the interval, then that one local min, oh, come on, that one local minimum is also a global minimum. I don't know why this right side of the screen doesn't like to write very good. Okay, so what's that telling me? If I want to find out how to minimize average cost or find the global minimum of average cost, we have two ways we can do it. You can use the derivative of average cost, find the critical point, and make sure that find out if it is a global minimum, or you can set the average cost equal to the marginal cost, or C prime of Q, and solve for Q. So either way works. Probably most of the time this one is the nicer way, less algebra for solving, but that's your choice. Okay, so let's look at this visually. Okay, so here's my cost function. Okay, I can see that at production level of 0, we do have a cost. So this is our fixed cost. Remember, our y-intercept would be our fixed cost at a production level of 0. Okay, and then, so let's talk about if we're at a production level of 50, for example. Okay, so here's 50. Okay. So this point here is 50, 50 C of 50, right? So at a production level of 50, then we've got whatever our cost is to produce those 50 units. Okay, the average cost then is the slope of the line connecting the origin to the cost function at that production level. So basically, if I draw a line from the origin to that point, then the slope of that line is the average cost per item, or the cost per item when you're producing 50 items. Okay, so let's verify that. Let's find the slope of that line between the origin and that point at our production level of 50. Okay, so change in y over change in x. So the cost to produce those 50 items, total cost, minus 0 over 50 minus 0, basically gives me the total cost for 50 items divided by 50, which is the average cost to produce 50 items. Okay, so this line here has a slope of the average cost to produce 50 items. Okay. Oops, I guess they're connected. Okay, the marginal cost, then we know marginal means slope of the tangent line. So the marginal cost is the slope of the tangent line to the cost function at that point. So if I'm talking about the marginal cost at 50 items, then it would be this line, the line drawn that is tangent to that point on the curve. So this line here, the slope would be the marginal cost at 50 item production. Okay, so both of them are slopes. Average cost, cost per item. Marginal cost, cost per item. They have the same units. Okay, so what do we want? We want to know what's the production level, what's that Q value where the line connecting the origin to that point, the average cost, and the tangent line to the curve, the marginal cost, are the same. So average cost is at a minimum when the production level where the average cost is the lowest. Okay, that's what we're looking at. So at this point, this is where the average cost is the lowest. So there's the line that connects the origin to that point. That's my average cost. Notice that that line is also tangent to the cost curve at that point. So that's what we're looking for. The line that goes from the origin from the origin and is tangent to the cost function graph, that will be where our average cost is at a minimum. And there you go. That's how we talk about minimizing average cost.